Welcome to another episode from the Ed of Ed.
But there are certain caliber of individual that's all they use is cast iron.
Maybe we should talk about cast iron accessories.
Yes.
So, like, for example, our cast iron set that we got came with that glove, the heat glove.
A heat glove.
And like a hooky thing.
To remove the lid off the cast iron. Now we got a cook set that's designed for outdoor cooking, which it is used.
And bread and wine are entirely transformed, and then it's given to us to eat. I remember having an image one time of the angels watching us. I remember just in my mind just seeing like the angels watching, like all the people down at American Park, and then the daytime began.
Cautious of how and where you lift it and put it once you're done.
You'll see a lot of
Scour the bottom of all of creation because it is not. It's frowned upon to use steel wool on a cast iron because you can break apart or remove that seasoning that is being layered into the bottom of the pan. That over time create that non-stick layer, that natural non-stick layer.
Okay, so this project I basically finished a couple years ago and produced a video which I got like 90% done on these homemade air capacitors for like crystal radios and so forth. They're 3D printed devices. They're really quite nice, but right around the time I was finishing the video, that's when I noticed that the capacitors were having some odd little behaviors. And it turns out the premise behind them is that there's a piece of weather stripping that's at the bottom of these guys that is used as a bus, basically a strip of aluminum foil and a piece of foam to connect all of these strips of aluminum plates together. And the problem is the foam, has a bit of a memory to it, and it starts to lose its elasticity and doesn't press the foil up against the plates as well. And so the capacitance of the capacitors was starting to drift down a bit over time. And then unfortunately the glue I thought, which was pretty darn good glue, Gorilla Glue I've used for all kinds of stuff, turns out to not adhere quite as well as I thought, and so things like a plate fell out and so forth. And it probably was also exacerbating the problem with the continuity of the strip of aluminum foil being compressed by a piece of foam. So I kind of held off on finishing the video and releasing this, thinking I'll get around to eventually, doing some little improvements to it and then being able to have this perfect capacitor to share with you folks. And of course I haven't got around to it. During the about half year or so that I used them, they worked great, and then shortly after that is when I was noticing the performance degradation. So I thought I'd just give up on sitting on this video and just go ahead and present it warts and all, and knowing that there's lots of creative people out there and they might be able to come up with some minor improvements on my design. One thing I had initially thought of doing was simply something like steel wool, or in this case bronze wool, in the strip, and instead of say the foam. And also there's conductive. Another thing I was thinking of, I ordered this from Amazon. I actually ordered two versions of the copper foil tape. Supposedly the adhesive side is conductive too, and I'm not really sure. I haven't yet to get around to trying it. I had one that was like a double-sided and one that was a single-sided. Amazon managed to deliver me this one, and the other one they delivered to some other house. Plainly it was not my porch that the photo was in, and they've never responded to my never getting the tape, and I haven't got around to it. Of course, I'm always the biggest problem for me is too many interesting projects and too many shiny things and never really quite completing things. It's amazing I get any few videos I ever do post on my channel, and the stuff posted on Thingiverse. So anyhow, So bear with me on this video. It's probably not my best video. There's a lot of little details to deal with, and realize that they're not perfect, but they're a lot of fun. Even if I figured they probably would only last maybe a few years, that they'd have conductivity issues with the foam kind of losing its elasticity and compressing the foam, and then the aluminum foil up against the plates. And also, maybe they might have oxidization issues. But I think the basis of the 3D printed frame and the overall design is meritorious enough to let people give it a try if they want. They might be able to do some improvements. The premise behind this was simply that it was really easy to just glue all these guys in, use a strip of foam and some aluminum foil, and you'd make this thing that was electrically conductive and very easy to make with very little in the way of tools and specialty assembly and so forth. And I must say, during the half year anyways that I used them and played around with them, or maybe it was a little bit more than a half year, they work great and they were just fun. It's really quite magical to have something that's just a bunch of series of aluminum plates and some 3D printed parts, produce a radio signal, tune in your radio, and it works. And it's just another one of those things where for very little effort, thanks to 3D printing, you can do some really fun stuff. So anyhows, take it as it is. It's not too hard a project. Gonna have to come up with some improvements. I didn't get very far in this other idea, which I don't really like all that much, is a copper bus bar, which is just strips of bare copper wire with no insulation on it, and then just tie wrapping them kind of in place. And I started on it. It looked very burdensome. I might follow up on that and post that. I think I only got this one part designed and printed. I never did the other one, but it's kind of a thought too, as a backup. So anyhows, off with the video here, as it's otherwise have been shown a few years ago anyways, and hopefully you enjoy it. And if anything at all, most people don't wind up actually producing these projects, but are just simply watching them for the fun and inspiration. And the few folks that actually do produce them, if you do make one, let me know what your solution is and how well they work. I'm kind of curious as to how well they work, because I think it's been kind of fun, and I would like to follow up on this a little bit further. I have some designs with some gear reductions on them and some other stuff I did some stuff on, and if there's any real further interest on this stuff, I may follow up and finish those projects up and maybe do some further stuff on this after all. So anyhows, on with the show, and thanks for watching. Welcome to another episode from the Ed of Ed.
For Miami, what the Hurricanes are going to face here. And I also think Houston's offense.
And then it's going to be touring around the country.
Okay, so if you ever wanted to play with your own crystal radio or homebrew radio set, here's a thought for you folks, is to make your own homemade capacitors too. The idea being that it's getting kind of hard to find these little air radio capacitors anymore. You can scrap something out of an old radio, such as this Crosley radio set, but it's kind of a shame to scrap a radio if it still has the potential to be repaired and rebuilt. In this case, this Crosley was just so far gone. So the idea here is I have made my own 3D printed capacitor, which is this gray guy with the big plates, square, and it's definitely odd looking. And it's just designed to be as simple and easy to make, and it has roughly the same capacitance as the commercially made capacitors. In this case, we have a nice little modern capacitor you can buy from some vendor on Amazon, and I think they're about $30. And it runs a typical air capacitance range for a radio of about 30 to about 360 is usually kind of the advertised range for most of the radio air capacitors. This one measures up around close to 400 picofarads. And then the old Crosley radio here is the same thing. You can see the Crosley capacitor is quite a bit larger. And it might have been back in the day when they couldn't make things quite as precisely small, or more likely because it had to operate at much higher voltages. Those old vacuum tube radios were at high voltages, whereas the little modern capacitors, probably would have been really meant for transistor level voltages. So if you look at my homebrew capacitor here, it's a pretty large thing, and I've designed it mainly to make certain that it'd be reliable to make. And so I didn't worry about the size, physical size of it. I just wanted something that would come out about the same capacitance range as a nice commercial, circular round disc capacitor, and not really worry about the size and shape of the thing. And the idea here is using square cut pieces of sheet metal. It'd be so much easier just to cut the metal and not have to worry about the strange shape. Now this capacitor is a prototype capacitor. It's on the table here, and the early one had the same number of plates, but they're further apart. You'll notice the one closer to the camera here, the spacing's a little bit tighter, and there's a little more space in the back where it isn't being used. And it's amazing how just putting the plates a little bit closer together, even in this homemade capacitor system, would produce a higher capacitance. This first prototype with the spacing further apart is probably almost half the capacitance of the other capacitor. And so, as you can imagine, if you were to 3D print your own design with still tighter spacing, you could with this design produce a capacitor that could have quite a bit more capacitance than the typical radio variable air capacitor. The big reason I designed it this way is I wanted to make certain that the sheet metal, which is just flashing sheet metal, aluminum sheet metal of about 15 thousandths, it's not very flat or true and precise, and so I wanted to make certain the plates wouldn't short together. Okay, so I thought I'd give you a quick little rundown on the CAD model as far as making some minor adjustments. I've included a little test coupon, and I'd recommend printing that just to make certain that your printer will be able to print these narrow little slots that the sheet metal goes into. My 3D printer, I've found I need to add about 15 thousandths to the dimensions for things that will slide together, say a tube going into a hole, or say in this case a piece of sheet metal going into a slot. And the sheet metal I'm using is about 12 thousandths thick, so I add 15 thousandths to that, and then a few extra thousandths just to make certain everything fits loosely enough that everything goes together easily for the glue and so forth. Say for instance you had sheet metal was a little bit thicker, say 35 thousandths. You could just change this one value here, and then all of the other slots will follow, and then you'll notice that that's reduced the spacing to the end here. However, on the other hand, the design I have is very conservative. I have a lot of space between my plates because I'm worried about the sheet metal having bows and curls to it. I'm also just not very concerned about the capacitor being really oversized for its capacitance. It's just a hobby project here. It's not like it's going to be a commercial product that has to go in a cabinet or something like that. And so, for instance, you could reduce the spacing between the plates because, say, maybe your sheet metal's a little bit thicker, or you want a little more capacitance, and you probably easily reduce the gap between the plates quite a bit. And so now, even though I've increased the width of the slots and reduced the plate spacing, I actually have quite a bit of real estate back here. So now this capacitor would have higher capacitance, but you might take a little bit more of a risk that the plates, if they're not really truly flat, might short against each other and so forth. Also, if you want, I guess you could add some more slots here. Okay, opening the 3D printer slicer software of your choice. Your slicer might say that the part is manifolded. The parts print just fine, so nothing to worry about there. If your printer is able to print PLA plastic and you get good results, you'll get good results with these parts. There's absolutely nothing to them. They're very, very simple. Nothing really go wrong here that I've been able to find. They print very nicely, very straightforward. So whatever settings you use for PLA, I would simply recommend PLA. There's really nothing, necessary in the way of any more exotic materials. PLA works just fine. There's no need for any sort of supports or anything like that. There's nothing fancy about this, and the part will print, I think, just fine. There's no need for exotic materials or particularly exotic settings. It's just fairly straightforward. Okay, so now this is probably the part that's going to be the hardest for folks. It's the sheet metal part. I went with aluminum flashing. It's about 10 thousandths thick, and you can get it at your local home improvement store, and it's really economical. This is like, I don't know, less than 20 bucks, and it will make a lot of capacitors if you can get through the first bit here, which is kind of dangerous. Yeah, it's kind of under compression there, so carefully cut that sheet metal open. And I have a pretty nice machine shop that has a lot of tools and equipment. This was kind of the part of this project I was debating whether or not, I'd bother to share it with folks as far as, being a home brew do-it-yourself project. Because how many people have a nice sheet metal shear like I do? And the reality is you could probably still cut this stuff with, good tin snips, or you could probably maybe have somebody that you know has a sheet metal shear, or most of all, if you're really a do-it-yourselfer, you probably really just want to invest in a small one. The one I got here is, I think, a 30-inch Harbor Freight, all three in one thing, and I don't remember what it was, $300 maybe 20 years ago. I don't know what they go for today, but they're probably not too much more expensive, I hope. And you can get a shorter version that's only like a foot long, and then there's other models of sheet metal shears out there. Anyways, the sheet metal is got quite of a curl to it, so by doing this kind of backwards curling operation here, you can kind of get a lot of that curl out. And then, at least in the case of the sheet metal shear, I needed to cut it to manageable lengths that I could cut on the shear. And like I say, you could probably use maybe a scroll saw or some way of cutting out this stuff without having too jagged an edge. So you cut it out to a reasonable length, and then I've got a little stop here made out of a piece of plastic. Just cut it to nice little strips, and you can really go to town with a little cheap sheet metal shear like this, especially on this really light sheet metal. It's really easy to work with, and that's the other reason I chose it. It's really easy to shear with just the lightest tools, and it's really easy to form, and it's super inexpensive. Initially for the first prototype, I just happened to have some sheet metal left over from a project, so that's what kind of inspired this. And of course, for the next capacitor, I had to go buy some more sheet metal, and luckily it's a good value, for the money as far as what you need it for, which is, for a capacitor, you don't need any structural strength. You just want the sheet metal to be reasonably flat and true. And by the time you play around with this stuff a little bit, you'll get it reasonably close, flat, and good enough for the job, especially if the design's been kind of carefully designed to account for the imperfections, and you don't mind the capacitor being a bit on the oversized scale for its capacitance. And though after you cut all those strips to about 2 inches, then you'll want to cut them to the final length, which is, I believe, 2.5 inches. You'll in the Thingiverse site, I put the files for this guy. I'll have a bunch of drawings as far as dimensional drawings and prints that you can go by just take a look at all that stuff also. And like I say, with the sheet metal shear here, I can really get kind of spoiled with the shear. You can really go to town with this thing. Other ideas beyond tin snips would be to maybe roughly cut these things and then do a final dimension by stacking them all together and doing a final dimensional cut by some other process to get them all the same. And also, once again, the sheet metal, as long as it's kind of reasonably close to the same dimension, probably doesn't matter so much. The big thing here is that it's a really good idea to get all those edges nicely deburred and smooth. Here I got it's a little rubber wheel that has an abrasive material in it, and it's meant for aluminum, non-ferrous metals. And the big key here would be there's an aluminum foil strip that's used as the bus bar, basically, with a piece of foam that's backing it to kind of spring load it into the strips, and you want to make sure that edge is nice and smooth. And so once you get all your pieces of sheet metal cut, you'll notice that they're all not really truly flat, and you got to do a little bit of tweaking here. You're gonna have to be patient and kind of look through them a little bit, and I like kind of bending them on the side of the table here and get that last little bit of bow out, kind of check it on the table and see if you can see any further bow or springiness left. And it's just kind of one of those quiet evenings of fiddling with little details like that, and ultimately the project can be quite rewarding if you just take a little patience and do little minor craftsman efforts like this. Next thing is, after you flatten up all those pieces of sheet metal, you want to kind of see how they fit in the 3D printed part. And you definitely don't want to put the parts in for the first time with the glue in place and find out that there's little blobs and imperfections inside those grooves. So, and also this way you can kind of double check to see if the plates are really flat. When you see them all stacked in there and comparing them to each other, you might be able to see there's a bit of a flaw in one or the other. Or you might be able to prefer a particular direction and spin it around and so forth. So once again, it's a good thing because you can practice how you put these in, meaning that when you've got the glue on the surfaces, you have a finite amount of time to play with the glue, and it's obviously going to be a bit of a mess at that point. And you don't have the piece of aluminum foil and the little piece of weather strip that sits in that groove to kind of fight with you while you're trying to figure this all out. And then, like here, you got the blob of plastic that you got to clean out and check that all out. And then once you got these guys all done, you can stack that particular stack for that particular side of the capacitor off to one side. And then it's just 3/8 weather stripping that you can buy at your local home improvement place. It's just a foam strip that fits comfortably into that groove there. And then that little white paper that's on top, that just keeps the next layer from sticking it to the next guy, so you can peel that little bit off and cut that piece of foam to length there. It's not a particularly precise operation, just get it right to the end there. Next thing is the bus bar itself, which is just a piece of common aluminum cooking foil. And the idea here is you want it to be just a little bit narrower than that strip of foam, and at least 3 or 4 wrappings, turns, folds of the sheet metal, so that say the aluminum strips were to cut into the foil a little bit, you'd have several little bits of foil left to go through, and it won't cut through all the layers, and you have a good conductive strip all the way across with very little loss. It's nice to use a ruler here and kind of gauge it and kind of get that edge creased and just kind of fold it along. And then once you get a couple folds in, it folds quicker because each fold then kind of plays off of the previous fold, and it continues to be nice and precise. Of course, the next thing you got to do is cut this, and the aluminum foil you can cut with a pair of scissors if you don't mind ruining your pair of scissors a little bit, because the aluminum foil will almost certainly dull the scissors a bit, so don't use your best scissors here. Yeah, maybe get your scissors that are a little on the duller side and still good for at least aluminum foil. Now, I like to use Gorilla Glue. It's the interesting thing about this stuff is it's water activated, so you can put the stuff on, and it won't really start curing and solidifying all that quickly until you expose it to a bit of water. And the other nice thing about the Gorilla Glue is it kind of foams up a bit, so it'll expand into these grooves and fill in the space a bit more than it would be, say, some other glue. And you don't have to worry about it being something that you kind of have to get some kind of tacky up to some point and then stick it together like contact cement or any sort of two-part epoxy or something like that. It works pretty well. It's fairly forgiving, easy to work with stuff. And like I say, because it foams up a bit, you don't want to put any more than you absolutely have to. So what I'll do is I'll put a number of little beads as thin as I can, and then I gotta somehow get that glue into the grooves and really off the surface, because it's not on the surface obviously where you want it down in the grooves. So I'll take a piece of plastic, like cutting the lid of an old yogurt lid, and it's a nice pliable plastic, and get it to kind of squeegee down into those grooves there, and basically thin it off the surface where you don't really need it, down into the grooves where you really do. Get it in there nice and even. And because it's, like I say, water activated, you got a fair amount of time to kind of work with this stuff before it comes, you know, kind of thick and gooey and viscous and hard to work with. Then the next thing is to be really important is don't forget that aluminum strip of foil. That's going to be your bus bar, and if you glue this in, obviously the magic of how this works would be gone. So you keep the foil kind of in the back there, and as you keep putting in these little strips, the length of the foil will slowly be shortened as it gets folded a little bit down into the foam. So you'll kind of have to fight that strip as it gets pressed in and popped out a little bit and pressed in, and it'll slowly shorten as it gets drawn further and further down into each of those grooves. And so you want to make certain that when you made that aluminum bus strip that it's way longer than you need. And then as you apply these pieces of sheet metal, what I have is a little shallow container of water, which may be a little excessive. I might have really gotten by with just a really well dampened towel to kind of just rub the plates against rather than just dunking them. I do shake the water off, and my glue joints seem to have done just fine this way. It's still kind of a work in progress, but the idea is you want the Gorilla Glue to then have this little bit of water to start its chemical reaction to solidify. And once again, it's just kind of one of those tedious little tasks that require patience and just kind of diligent attention to detail here. As you build up and put these strips in, you'll have to kind of keep one hand, kind of keep them in place, because the foam wants to push the plates back up, and you also want to make certain that the plates, you know, don't saw or cut that foil. So it's kind of just a gentle, constant little maneuver here to keep the next plate in, move your hand over, put the next plate in, and apply that little bit of force that once the plate's in there and set, that it stays in place until you can get the next plate in. Otherwise, once you get the hang of it, it's pretty quick and easy. The other thing is, before you start all this gluing operation, you'll want to make certain you have some sort of vice clamps of some sort, and scraps of material to kind of distribute the force across all these little plates. Maybe if you had a strip of fairly dense foam that you could then sandwich between the compressing plate and all these little plates, so that you kind of distribute the force across all these plates, that'd probably be kind of nice. I just use some bits of scrap and just very, very lightly compressed, as lightly as I could get away with. used a fairly heavy piece of steel here, or aluminum, and then very gently clamped. And I just observed when I went to apply the C-clamp here that the most force I would apply on it is the guy with that was the proudest sticking up wouldn't get bowed too much, while the guys that are the shortest hopefully still have at least some modest contact. And then once they're done here, you can pull this guy out and start dealing with the next little detail, which is looking at the bus bar here, which you need to trim that little bit of excess off. And here you got to be kind of careful. This little bus bar of aluminum foil is kind of precious at this point, being that all those plates are glued in place, and you certainly don't want to damage that foil. But you put a little strip, you cut a little slot in it, and then down that slot you'll put a screw. And so you put a large washer on one side and put it through the 3D printed part here where the bus connection is going to be, and then through that little slot, and then you'll put another large washer that basically sandwiches the slotted tongue of a piece of foil basically, and keep that all in place. And then make certain that that screw you're using, like I say, it's a 440 in this case, a metric equivalent, whatever that would be. Make certain that that screw has a little bit of extra length so you can put any sort of a terminal connector you want, and then another screw. And then it's just a matter of lightly turning the screw and tightening it without the nut spinning and possibly tearing your foil or anything like that, but making a good electrical connection. It will be reliable. Next thing is to test the continuity of this guy. Just hook up a volt ohm meter and set it to continuity, and just ring out all those connections, make certain that the foil is really being pushed up against all those strips, and you got a good electrical connection. Admittedly, this is probably the weakest part of the design. I suppose these capacitors, if they're exposed to a lot of humidity, they might corrode, and eventually the conductivity might become a little bit questionable. But hopefully you'll get a good bit of service out of this guy, and it'll be worth playing with. Next thing is you gotta tap the little bushings. The shaft itself for rotating the rotator is a 1/4 inch piece of all thread, and you need some sort of a bushing that can allow that shaft to rotate without, of course, the threads grinding away at the plastic. So this is what this does, is basically just a bearing. Bearing block stops, and along with some locking nuts on the threaded rod, and you can adjust the rotor back and forth. Now, one thing I forgot to do was remount the holes where the shaft is going to be going. So his is a it needs to be just a little bit bigger than the hole, so it'll clean it up and still allow the bushings to freely, smoothly go in and not have a lot of play. And these look pretty good. Now it's time to do the awkward bit of assembly, which is you put in a nut that's going to basically compress one of the arms of the rotor, and that will allow the positioning of the rotor as far as linearly along the threaded rod, and it also, of course, allows the torquing of the rotor. It allows it to turn, of course. And the nice thing about these bushings is that once you get them threaded and locked, they should hold up pretty well. I mean, I suppose if you use this capacitor design quite a lot and you were to play and tune the radio for, you know, years on end, you might eventually wear out these bushings. But I suspect for the, you know, the life of just playing around with this as being kind of a hobby toy project, I wouldn't expect that the bushings will wear out significantly or need a whole lot of adjustments. Basically just getting that threaded rod in there and then put on the next nut that will capture one of those arms. Just a nut on either side on, say, the forward arm of the rotor is quite sufficient. And it's just a matter of cranking it in till you get that front bushing into its bearing block and its little flange stopped against its surface, and then you can put the next bushing, putting the next bushing in. And of course, once you get this bushing in more or less lightly stopped up against its bearing block bore, you'll want to put another 1/4-20 nut. And then you got to start kind of dialing in lightly adjust the nuts on either side of the rotor arm and loosen one side, turn the other side a little bit, and keep looking at the gap between the plates until you get the gaps between the plates nice and even. And you'll notice that on the rotor, there's one extra plate on the rotor over the stator, the stationary plates. So you'll have one plate sticking out one side on the front and one sticking out of the back side on the side that moves. Next thing are these really handy brass meltable inserts. They're little threaded nuts basically that are designed to melt into the bores where the screws go. And you could do it, you know, any other way with maybe screws or nuts and what have you. But I really like using these guys. It makes it so much handier, and they're cheap. They don't cost a whole lot. You set your soldering iron to a modest temperature. I've found somewhere between 420 and 500, 600 degrees, pretty good. I tend to set mine a little bit on the low side. I notice some people, they really let their soldering iron rip to the point where the plastic's starting to smoke and boil. I don't think you need to go quite that high. Just enough that you kind of gently get that plastic in there. At the lower temperature, you have a little more control over it. Just slowly push it in. Then what I like to do is when I'm getting close to the last little bit of seating location, what I'll do is I'll press it against a heat sink, like a chunk of aluminum, and I'll press that in so that it's flush with the face of the plastic part, and it also sucks the last little bit of heat out, so it kind of solidifies that plastic and reduces the amount of stress on the plastic. And then there's a number of different mount points on the capacitor. You can mount this thing with its face to the back of a panel, you can mount it to the side, or you can mount it to the bottom. They all have holes of the same size, 4 of them, that these 632 melt-in inserts can go into. So there's, you know, 3 options as far as places you want to put mount points on for your capacitor, however you want to mount it. There's quite a variety of possibilities here. So it's the same thing. You heat the plastic up and melt it with the solder iron, heating the brass insert, and you get just shy of the plane. And then I like a aluminum block or some heat sink to press that last little bit in, get it nice and flush, and then suck that little bit of heat out so that plastic solidifies in a nice set position. And it's just rinse and repeat. Once you get one, get all 4. Same process. The thought might have been, if you know you're confident enough that you're gluing these parts in and everything else was going to go okay, it might be better actually to glue or to melt the screws in before you put any of the aluminum parts in. That way you can kind of reach in there and not have to worry about damaging the delicate aluminum fins. Being I've now made a number of these capacitors, I'll probably just do it that way. I've got the skill down to where I know that I can make these quite reliably, so I'll probably do things like make certain I remount those holes for the all thread for the rotator shaft, and then the mount screws, so that there's one less thing to go wrong than, you know, trying to do these little operations with those delicate pieces of sheet metal. Although if you're careful, you know, have the thing closed like that, you're really not likely to damage anything. Also, I've noticed that once you've melted these plastic, these inserts into the plastic. Sometimes, say on the knob, for instance, some of the plastic will kind of melt out in front of the insert and will kind of block where the thread is, reaches out. When you go to put a screw in or something like that, there may be some plastic in the back, so you might find that you need to use a tap to just kind of ream and clean out the threads a little bit with the plastic that might have extruded out behind it. A little minor detail there. Sometimes I think the brass inserts distort a little bit from the heat, and so reaming them out with a tap helps. A long time ago, I got a whole bunch of this kind of not really great quality plastic for free at a plastic shop. They were just tossing out tons of this stuff, so I kind of abused the privilege of getting free plastic, and I got a ton of this plastic that over the years I've tried to figure out what I can do with for various projects. So my guess is that if you want to make a some sort of a little stand or frame to put your capacitor in, you might use wood or something like that, whatever is readily available. But I just happen to find that this plastic that is a 1/2 inch and 1/4 inch thick works out very nicely for these sort of projects, and I just happen to have a ton of it. And it's easy enough to saw, so a little table saw action here, and be careful and cut it all up, and it goes real quick and easy. Obviously, whatever you want to do for your capacitor as far as mounts go, this is just kind of a suggested idea at this point. I have no idea what folks might actually do with these capacitors. No, if actual, hobby projects goes. And once you got your big pile of plastic, you can drill all these holes. And I've included in the files some PDFs that are 100% scale. So if you print out the piece of paper and you position it right, say in this case 3 inches off the edge, you can use it as a nice template. The big thing is to make certain your paper printer is printing the correct scale, so you know the dimensions of these holes in the CAD model. Just kind of take a ruler to the piece of paper and make certain that your printer actually printed these to 100% scale and that they're all correct. And that way it just makes drilling these parts so much easier. When I have to eyeball hand drill stuff, mark and measure stuff, I darned if I can ever quite get everything just exactly right either. So a little paper guide like this really makes life a whole lot easier. Then once you got everybody all drilled, you can screw it together. I like using some just cheap, 1.25 inch long drywall finishing screws. They're quite nice. And then I countersunk all the holes. So when I go to put this guy together, I use the drywall screws to mount the front plate to the base plate. And then to mount the capacitor, I use some 632 flathead machine screws that are 1/2 inch long. And then later on, when I put a paper dial applique on, those screws are sit nice and flat, and the paper dial can sit on there nice and flush, and it just adds a nice little extra finishing detail to the little mount plates. And the whole idea is just to have this whole thing modular, so I can have all these capacitors and components modular, so I can mix and match all kinds of different designs together of circuit designs. We're ready to start assembling this guy. Basically excluding the waiting for the glue to dry. It's just a weekend, easy weekend project. The 3D printed parts are the base frame is maybe a 5-hour print at just a normal standard kind of print resolution, and the rotors maybe 2 hours, 2.5 hours. The cutting of the little modular frame here to just kind of mount everything on, that's maybe an hour's worth of work, and then it's a few hours work to glue all these parts together and deburr and cut the sheet metal. And so a few hours each day over a weekend, and you got yourself a pretty nice capacitor that is quite satisfying to have built yourself. Added extra touch is this little applique print. I've included that in the CAD and solid 3D print files. It's basically what I did is I took my capacitance meter and several of my capacitors and just ran back and forth between swinging the arm in and out, took different values, and then averaged that all out. Like I say, this is a homebrew capacitor. It's not nearly as precise and repeatable as the commercial ones. There's definitely some variation between them. And so this is just a rough average between the capacitors in each of the runs. But it gives you an idea of what the capacitance is on the angles. Your capacitor almost certainly won't be exactly like mine. But for kind of a hobbyist DIY, it's a nice little extra thing to kind of know what the capacitance is at what angle, or at least get a reasonably good feel of what it all is. And then you can kind of do some theory and design and kind of learn radio without it being just kind of this little black magic art thing where you don't really know a lot of the very specific details. It's nice to run a little bit of theory and say, if I have this much capacitance and this inductance, I should wind up with this kind of frequency. And in this case, it's kind of done for you as far as a general idea of what the capacitance, and later on when I'm doing my inductors, what the inductors are at. And with that, you can dial this to these positions and do a little quick bit of math and look up to see is your circuit oscillating like you would expect it would. And it's really quite satisfying, gratifying. And it's nice, easy to read display, so it's fun to play with. You can log your settings and so forth as you play with your capacitor.